Good morning, everybody. Welcome to the partial differential equation series. I would like to start this series by talking about the advection diffusion equation, or it can call ADE if you encounter it as anyone who reading articles and you see they talking about ADEs. This is the one, advection diffusion equation. So advection diffusion equation, they describe the velocity profile or the concentration profile. So in this case, we interest in the velocity profile through space and time, okay, of a particle, right? And that particle is under the influence of dispersion and I think advection. Okay, so this is more like a so in chemical engineering we have two classes. We cover this in fluid mechanics and transport phenomena. Yeah, so the general idea is that you interest in the velocity profile of the particle, so see how it changed. So let's go ahead and jump right into it. So the question I'm covering today is actually from a paper. What's the paper name? I will link it down below for y'all and the description link. But the author is let me see. Let me make sure I write his name correctly. Canbolat et al. Okay, et al means other people. And it's been published in 2019. Okay. I'll write link below in description. Okay. So what are we interested in? We're interested in this video, we're not entirely interested in how to solve it, but we are interested in reducing it to something we can solve. Okay, so let me write my goal. So is the goal this problem? So goal: convert the partial differential equation, or the PDE, into something we can solve. Okay, so I'm not going to go over how to solve it completely, but let's go ahead and convert it to something that we can solve. So what is the equation? Okay, y'all have wait 3 minutes for the introduction of the equation, right? So the equation says that it's a partial differential equation. First of all, it says the partial of u with respect to t, which is the the velocity gradient with respect to time, okay, plus c times the partial of u with respect to x equal to mu times the partial square of u, or the second partial derivative of u respect to x. Okay, this is the equation we're interested in. And to the best of my knowledge, y'all can check it in the paper. So C is the concentration, and I think mu is kinematic viscosity. Okay. And the thing is C and mu. C and everyone can use called V. It does not depend on x or t. Okay, so what it means is that in this case, the c term right here and the mu terms right here, you can treat it as a constant. Okay, so I have stated gone before that we want to convert this to something we can solve, right? So what's the proposal? So conversion proposal. Okay, so so we start with this equation, right? We start with our original equation. Partial u is partial t plus c times partial u over partial x equal to mu times partial u square over partial x square. Okay, so this is our proposal. Our proposal is we want to we're gonna substitute, right? We're gonna substitute u as function xt is equal to g as a function xt times something, or this something is a function of x and t, but I will write it so it make more sense. We hope that after doing a bunch of we do this transformation, it will obtain something like partial of t over partial t equal to mu v times partial square t over partial x square. Yes, guys, this right here turn to this right here. And the equation in blue, you see the partial in blue, is something we can solve. This is, we can solve this PD, via separation of variable. Okay. And this time we wouldn't worry about the boundary condition, but we just want to convert something like this. So in summary, we have the original ADA, advection diffusion equation, right? We want to substitute u equal to gxt times something. And hopefully after we find that thing, we substitute in and we obtain blue, which is a partial differential equation can be solved via separation of variable. Okay, so right here, we hope to find something. Okay, it's this thing. So in the next video, I will show you guys how to find it. Okay, and hopefully it will be very interesting to see all the steps to obtain this beautiful expression. Okay, I appreciate everyone's attention, and I will see you in the next video.